My name is Pranam Padi, and this is my Physics 2211 Motion of a Falling Object lab report. The goals of this lab were to observe an object moving in freefall and use Tracker to create an experimental model for the object's motion. Secondly, to create an accurate computer model of the object moving by using Newton's second law and the force of drag. Thirdly, to create another model using only the force of gravity without the force of drag this time. And then finally compare all three of the models and explain any similarities and differences noticed. So the concepts explored in this lab are Newton's second law, which can be seen by the equation final velocity equals initial velocity plus net force divided by mass times the change in time. The force of drag, which is the force of drag equals b times v squared. And then the force of gravity, which is force equals mass times gravity. And the procedure of this lab was to first record a video of an object moving in freefall, upload that video to Tracker and gather experimental data, then create an experimental model for the motion of the object, and then create two computational models for the motion of the object in GlowScript, one with the force of gravity and drag, and one with only force of gravity. Finally, compare all three of these models together to see how accurate the computational models are and discuss any findings. So my experimental data can be seen here. This is me dropping a paper bowl, and as you can see, all the data is in the bottom right corner, the time and the y, and then I have my axis set to measure all the y components as it drops to the bottom. And my graph of position versus time is being recorded here in Tracker as well. And from that, I gathered this experimental data, which was my observed position versus time of the object falling, and times in the x-axis and position of the y-axis. And as you can see, it's a negative curved slope. And this is my computational model, which I coded in GlowScript. So as you can see, the ball, the mass of the object was 1 gram. The initial position and initial velocity are updated here. And then gravity is the acceleration due to gravity is 9.8, so that's inserted there. And for the object with drag, I had to upload the drag constant, which is I had to guess and check and find that for mine to match the final position, it had to be 0.0322. And then in the graph without any drag, this value was just 0. And this was the computational model with only the force of gravity acting on it. So as you can see, it's an exponential, it's a parabolic slope in the negative direction, which makes sense since there's acceleration only due to gravity in the negative direction, no acceleration due to drag. And this was the computational model with force of gravity and force of drag. So as you can see in my case, this is almost a linear slope, which means that the force of drag equaled the force of gravity or close to it. And this is a graph of all three that plot on the same graph. And as you can see, my computational model with drag and gravity almost exactly matched my observed model, which means that in my real scenario, the drag was very close to being equal to the force of gravity, which would make it net force of 0 and a linear line. And free fall is just drag versus gravity, drag going in the positive y direction and gravity going in the negative y. And as I said, drag is almost equal to the gravity. And without drag, the object accelerates much faster, as you can see the orange one, which is just only gravity, because there's a net force in the negative y direction. And some sources of error are, as I said, too much drag in my lab, which is why there's such a big discrepancy. And there's movement in other directions, such as the x and z planes. And there's wind current from the AC, which could have accelerated the bowl or shifted in the other directions. And I could have just had human error and incorrectly labeled the points of mass. And so, what does it mean if what models predict a terminal velocity? So the computational model with gravity and drag predict a terminal velocity, and this can be seen by the position graph asymptoting somewhere on the y-axis, and on the velocity versus time graph that the GlowScript provides you with. Since the force up and force down are balanced, this would be the net force is 0. And if there's an initial velocity, the terminal velocity would change because of the initial velocity, and the terminal velocity would be reached faster as well, since the force of drag is increased when there's increased velocity. When graphed in GlowScript, what I predicted had happened, the terminal velocity changed and the terminal velocity was reached faster.